Hello. In this lecture, we'll define a regular value or a critical value of a differential map from an open subset of Rn to Rm. Okay. So now suppose you are given a differential map from R3 to R, and you take a regular value which lies in R, and if you take the inverse image of that regular value under that map, so then that will be a regular surface. So that is the thing we are going to show in this lecture. Okay, so let us begin. Yeah. Okay. So let us take a differential map. So let F be a differentiable map from U to Rm, where U is an open set in Rn. So F is a differentiable map. And also we assume, so this, and let us assume, so this N is greater than equals to M. Okay. So we say that a point P belonging to U is a critical point of F if the differential of this map F at the point Q is not a surjective map. So this will be defined from Rn to Rm is not a surjective map. Okay. And so this point, so the point FP is called the critical value of F, is called a critical value. So there can be several critical value of F, is called a critical value of F. So a point of Rm is which is not a critical value, which is not a critical value, is called is called a regular value of f. Okay, so now, so let us understand this by some examples. So let us take a function r to r. So fx equal to x square. Okay, and so f, it is a function from this r to r. Okay, and let us take the differential of this map. So differential at the point x, so it will be a linear map from R to R. So R treated as a R vector space. So what is this linear map? So dfx, okay. So so this is operating on a real number which is treated as a vector. And now you have the matrix of this map. Okay, so matrix here, it is just a single entry, it is there in the matrix to x, and then multiplied by this lambda. So it is just 2 lambda x. Okay, so yeah, so this dfx lambda is 2 lambda x. So this is a linear map. And so you want that this map dfx is surjective or not. Okay, so when it is surjective, so dfx is surjective. So if and only if so this map is not equal to 0. Okay, so now dfx is equal to 0 means the matrix of dfx is also 0. So this implies that uh, so this x is equal to 0. Okay, so dfx equals to 0 matrix means 2 lambda x equals to 0 for all value of lambda. Okay, and that is true only if this x is equal to 0. Okay, so at x equals to 0, so df0 is not surjective. Okay, so therefore, so this 0 is a critical point of f, and again f0 is equal to 0, so is also is a critical value of this f. Okay, so if I take the graph of this function, okay, so the critical point corresponds to this point. Okay, now let us take another example. So let us take fx y z equals to x square by a square plus y square by b square plus z square by c square. Okay, and okay, so in the earlier example, you note that, so if I take any other so any other x, so fx equals to x square, where this x is not equal to 0. So x is not equal to 0. So if I take fx, so let us take, so if I take r equals to x square and it is greater than 0, so this r is a regular value of this f. Okay. So now let us take this function fxyz equals to x square by a square plus y square by b square plus z square by c square. Okay. And now let us take the differential of this xyz. Okay. So here, so corresponding to this linear map, so what will be the matrix? So matrix will be the following. So this is my matrix of this linear map. And if I take any lambda 1, lambda 2, lambda 3, this matrix is acting on this vector lambda 1, lambda 2, lambda 3. And this will be 2 lambda 1 x a square plus 2 lambda 2 y b square plus 2 lambda 3 z b square. So this linear map, it is from R3 to R. Okay. So again, so df xy z. So here the dimension of the domain space is 3 and dimension of the codomain space is 1. So it is surjective if and only if this is not equal to 0 map. Okay. So therefore, so this dfxyz, so this is a 0 map. So if and only if, again, from here, so what we'll get, so this is 0 matrix means all this x and y z, so they will be equal to 0. Okay. So therefore, so 0 0 0 is a critical point. In fact, it is the critical point of, it is only one critical point you'll get. So this is a critical point of f. Okay. And 0 equals to f of, so this is a critical value of f. And if I take any positive number, so let r greater than 0. So r is a regular value of f. Okay. So now here, so this function, if I take inverse image of 1, or let us take inverse image of any positive number, so r is greater than 0. So this means that, so this is the inverse image. So note that this f inverse is just a notation. So it doesn't mean that f is a bijectional. So this is just notation. So f inverse r, so this is all those xyz belongs to R3 such that fxyz equal to R. And this set is nothing but set of all x, y, z such that x square plus by a square, y square by b square plus z square by c square is equal to r. Okay, so this inverse image f inverse r, so this will be an ellipsoid. So this will be the roughly the picture of this. Yeah. Okay, all right. So now our next theorem will be, so suppose if you take a regular value of the function f, so its inverse image, it will be a regular surface. Okay. So proposition. So let us take, so let f u to r be a differentiable map defined over an open set u in R3. So suppose A belongs to, or okay, let us take A. So A belongs to Fu is a regular value of F. Okay, so then the claim is, so then, so F inverse A is a regular surface, okay, in R3. Okay, so how do you show this thing? Okay. So how do you prove this thing? So let us take any arbitrary point in this F inverse A. So let P equals to x naught, y naught, z naught. It belongs to F inverse A. So this implies that Fp equal to f of x naught, y naught, z naught, z naught. So this is equal to A. Okay. And so this point P is not a critical point. So P is not a critical point. So implies, so this map, this differential map, so is surjective. Okay, so this is surjective. And so this map, it is a linear map from, is a linear map, and it is surjective. Okay, so this implies that, so this will imply that, so D of Fp, okay, is not a zero map. Okay, so this means that if I take D of F, okay, so which is So the matrix of this is del f del x at the point P. So del f del y at the point P, del f del z at the point P. Okay, so just take the grad of f. So this map is not a zero map. Okay, at the point P is not a zero map. So this means that because this differential it is not a zero map, so one of the partial derivative will be not equals to zero. So this implies, so one of the partial derivative is not equal to zero. Okay, so let us assume so del f del z evaluated at P is not equal to zero. Okay, yeah. Okay, so now so we'll apply implicit function theorem. So by implicit function theorem, so what we'll get? So there will exist a neighborhood, open neighborhood B of x naught, y naught, and open interval containing z naught such that the following happens. So there exists an open neighborhood B of x naught, y naught, and an open interval I containing z naught and a so by implicit function there exists these two open sets and a smooth map G from this B to I such that what? So G of x naught, y naught is equal to z naught. Okay. And for all xy belonging to this B, so f of xy comma gxy, so this will be equal to a. Okay, so this implies that so this xy gxy, it belongs to f inverse a. So for all xy belonging to this B. All right. Okay. Okay. So now, so this B, it is an, okay. So there exists an open neighborhood B of x naught, y naught in R2. And this open interval, it contains contained in R. Okay, so I is contained in R. All right. So we have a map G from this open set B to I, and f of xy comma gxy is equal to A. All right. Okay. Okay. So also now note that. So note that. So this x y comma gxy. So this also belongs to this product of these two open sets B cross I. Okay. So this B cross I is an open set in R3. Okay. So therefore, so this xy gxy, it belongs to F inverse A intersection P cross I. Okay. And now let us define a map. So let sigma be a map defined from this B to B intersection I intersection F inverse A. So how this is defined? So sigma of x, y is equal to x comma y gxy. Okay. So this sigma, yeah. So sigma is a graph of this function gxy. Okay. So here this is my B. So xy is varying here, and so this is my F inverse E intersection B cross I. So this point over here, coordinate of this point is xy comma gxy. Okay. So check that sigma is differentiable. Sigma is a homeomorphism onto its image. Okay, and T sigma restricted to any point xy in B is injective. So once we have expressed this sigma as a graph of function, so this automatically this T sigma will be injective. Okay, so this already we have done. So therefore, so this B sigma is a surface patch for F inverse A. Okay, so this shows that F inverse A. So we have taken an arbitrary point P in F inverse A, and now you can do it for every point. Okay. So therefore, so this F inverse A is a regular surface. Okay. So only note here, so this map G, it may not be smooth. So I have taken any differential map F. If that map F, it is a smooth, so then I'll get a smooth map G. So this is not required. So here I'll get a differentiable map G from V to I. Okay. So F inverse A is a regular surface. Okay. So now again, if I go back to that example, so if I take fxy z equals to x square plus y square plus y square by b square plus z square by c square. Okay. So f inverse of, for instance, if I take 1, so f inverse of 1, so this uh, is a regular surface. Okay. And so this is exactly equal to all those xyz in R3 such that x square by a square plus y square by b square plus z square by c square is equal to 1. So this is a regular surface. Okay. All right. And so ellipsoid, so this is a regular surface. Okay. If I take a equal to b equal to c equal to 1, so then you'll get a sphere. So sphere, it is a regular surface. Okay. And now if I take, let us take the function. So let hxy equal to x square plus y square. Okay. So what will be my h inverse 1? So this is all those xyz in R3 such that x square plus y square is equal to 1. So again, you can show that this 1 is a regular value of this h. So this is a cylinder. This is this right circular cylinder in R3. So this is a cylinder. So this is a regular surface. Okay. So from here, so you can get many regular surfaces. Suppose you have a differential map from R3 to R. So you find the regular value of that function and take the inverse image. So you'll get a regular surface. Okay, so I'll stop here. We'll continue in the next class.